So hello everybody, welcome back. This is going to be our second online video lecture. So I hope you're getting used to the format. I hope it works for you. Again, there are going to be some technical kinks, but let's try to make the most of what we have here. With that said, let's jump right back into the Chapter 5 lecture, which has to do with circular motion. We just introduced this idea of centripetal acceleration, so an object that moves in a circle, even if it moves at a constant speed, is in fact accelerating, and that means there's some kind of force involved in that. So this is the example I want to go through next, and it has to do with something that you might have experienced if you've ever been to an amusement park before. This is an amusement park ride called the Gravitron. So the Gravitron consists of a large spinning cylinder. If this cylinder spins fast enough, riders will be pinned against the wall, and they're not going to slide down it, even if the floor drops away from them. Okay? So they're pinned against the wall, they're being supported, they're not sliding down the wall, even though, again, the floor has dropped away from underneath them. So suppose the radius of this particular ride is 8.80 meters, and there's a coefficient of static friction between the rider and the wall, which is equal to 0.350. What is the minimum speed of the ride so that riders will not slide down the wall? Okay, so before we get into the actual derivation of the formula and the calculation that goes into this, let's look at an animation, just so in case you've never been on a ride like this before, you know what I'm talking about. So there it is. This is a scene from The Simpsons, and here's just a still image of people on this ride in real life. Okay, so again, what we're going to do is find the minimum speed that this thing has to be rotating such that no one slides down the wall as it rotates. Okay, so for this, we're going to go ahead and go to the document cam. I don't have a camera operator with me today, so I'm going to work everything out on paper right here. And what we're going to start with is just a basic drawing of what's going on. So we have some kind of cylinder, looks like this. And here's our rider. This is the person on the ride. And this thing is rotating, of course, so let's indicate that. And since we're interested in how fast this thing has to be moving, it's good to start by getting a sense of what the forces involved are. So let's draw a free body diagram, FBD, of the rider. And let's think about what forces we have, but before we do that, let's draw a coordinate system that shows the different directions of motion for this rider. So we'll have the y direction be pointing straight up, and then we'll have the r direction be pointing in towards the center of the circle that the rider moves in. Remember, that's the radial direction, so it's going to point in towards the center of the circle. Okay, now this is going to represent the person, this dot right here. So on this, we're going to show all the different forces acting on the person. So the most obvious thing is going to be the weight. Force of gravity is always going to be present. There's another force we have to consider here, which is the normal force from the wall. So we have to think about this real carefully. The wall itself that the rider is pressed up against is actually oriented vertically like this. And remember, normal forces always act perpendicular to the surface, so what we're going to have here is actually a normal force that's pointing in towards the center of the circle like this. Okay? So there is our normal force, again, just pushing the rider in towards the center of the circle. And obviously this can't be it, because we need the rider to not be sliding down the wall. We don't want any kind of net vertical force or net force in the y direction, because the idea here is the rider is not sliding down the wall. So there has to be some kind of upward force that holds the rider there in place. And that upward force is actually static friction. Fs, the static friction from the wall, now points upwards, and it's holding the rider in place. So now that we have this basic idea straight in our heads, let's apply Newton's second law. To both directions. So we're going to have a Newton's second law equation for the y direction, and we're also going to have one for the r, or the radial direction. So I guess we could just start with the y direction. The net force acting on the rider in the y direction is equal to the mass of the rider times the acceleration in the y direction. What does that give us? Well, there are two forces. We have static friction, which is going up, so that's positive. We have the weight, which is going down, so that has a negative sign. So Fs minus W is how we talk about the sum of the y forces. On the other hand, or on the other side of the equation, I should say, we have m times ay, but the acceleration in the y direction we can set to 0. This thing is not accelerating, or this person is not accelerating vertically at all. That's the whole idea of the rider not sliding down the wall. There's no acceleration in the y direction. So we have Fs is equal to W. In other words, the static friction and the weight are equal in terms of their magnitudes, but weight is always equal to m times g, so there we have it. The static friction force, in order to hold the rider there, is equal to m times g. So we can do this again, apply Newton's second law, but this time to the radial direction. So we have the net force in the radial direction is the mass of the rider times ar. And now we have to ask ourselves, is there an acceleration in the radial direction? Well, of course there is. This is an example of centripetal acceleration. If the rider is moving in a circle at a constant speed, we have an acceleration in the r direction. And if you recall, the formula for that acceleration is equal to v squared divided by r. So here's what we're going to do. We're going to take, on the left side, the sum of all forces that act in the radial direction. But in this case, there's only one. It's the normal force that acts in the radial direction. What is that equal to? The mass of the rider times the acceleration, which again is v squared divided by r. So we've got two things to work with here. Static friction has to equal mg, and the normal force has to equal m times v squared over r. Those two things have to hold true if this rider is going to move in a circle at a constant speed and not slide down the wall. So there's one more piece of information to bring into this, which is, how does static friction actually work? It's given by an inequality. The force of static friction is always less than or equal to mus times n. Okay, so actually, let's put the expressions that we derived for Fs and for n into the inequality. So again, for Fs, we have m times g. For the normal force, we have m times v squared over r. So I just plugged in what we derived earlier into the static friction inequality. And notice something that happens. The mass drops out. And then we have an inequality which involves v, how fast the rider is moving. So if we do two things, we multiply through by r to get rid of it on this side, and we divide through by mus to get rid of it on this side, the inequality now looks like this: v squared greater than or equal to g times r divided by mu times s. And this is telling us that there's some kind of minimum speed here. The speed has to be greater than or equal to something, and that minimum speed is equal to the square root of gr divided by mus. What is this telling us? The rider has to be moving at least this fast, or they could be moving faster, in order to maintain circular motion and not slide down the wall. So here we go. Let's calculate that minimum speed. V min is equal to the square root of g, which is 9.8 meters per second squared, times the radius, which in this case is 8.80 meters, and then divide by that static friction coefficient, which is 0.350. Okay, and if you crunch these numbers, here's what you're going to get. The minimum speed is 15.697 meters per second, and then what we do here is we keep three significant figures given what we put into the formula. So this would round off to a nice 15.7 meters per second. That's the speed. So this is what we call a linear speed. It's how far you travel in meters divided by how long it took in seconds. We're also asked to find the speed in RPM. Okay, so in this case what we're doing is we're figuring out how many revolutions does the ride make every minute. Okay, that's RPM. So remember how this works. We have the speed. And remember that speed is nothing more than distance over time, which gives us, if we write this symbolically, v, our speed, is equal to the distance, but I'm going to set the distance equal to 2 pi times r, because 2 pi r is the circumference, and that's the distance you travel in one full rotation. If we divide that by the time it takes to do that, which is by definition the period, that's how long it takes to undergo one full rotation, we'll have this equation right here, which can then be rearranged to say t is equal to 2 pi r divided by v. That is going to give us the period of this rotation. So how long does it take the rider to make one full circle as he is on this ride? So we have 2 pi times the radius, which again is 8.80 meters, divided by, this v now is 15.697, keep 3 sig figs, meters per second. So when we make this calculation, we get the period, and the period is 3.522, keep 3 sig figs, seconds. That's how long it takes the ride to go around one full time. Okay, so we're not quite there yet. What we really want isn't a period, it's a frequency, it's f. And just remember that period and frequency are inverses of each other. In other words, frequency f is 1 divided by period, which is t. So here's what we have. It takes, for every 1 revolution we make, it takes 3.522 seconds. So that would be the frequency in units of revolutions per second. However, what we want is revolutions per minute, which means we're just going to do one quick unit conversion. There are 60 seconds in every 1 minute. Cancel out units of seconds. And here's our frequency. We get 17.03 revolutions per minute. Okay? And that rounds off to a nice 17.0 RPM. So that's how fast the ride is moving in terms of revolutions per minute and in terms of meters per second. So we answered the question. You need this minimum speed. Okay? If you go faster than that, you'll still have all the conditions met for the rider to stay on the wall and not slide down. But that's the minimum speed that's possible. Okay, so we go back to the lecture slides now. And then we're going to keep it moving and talk about a related question, which is turning a car. Okay, so think about this. If you want to turn your car, that is, you want to drive your car in a circular path of some kind, there has to be a net force acting on your car that's pointing radially inwards. Okay? This is what we call a centripetal force. Again, that means it's just pointing towards the center of the circle. If that's not there, you can't drive your car in a circle. Okay? You need that centripetal force to move your car in a circle. So the question is, how does this actually work? What is it that's providing that force that points in towards the center of the circle when you're driving your car on a curve like this? And it turns out the answer is static friction between the tires of your car and the road. Okay? Now, initially it might seem weird to think that static friction has anything to do with this because, of course, the car itself is moving. But what you want to think about instead is there any motion between the bottom of your tires and the road, which are in contact with each other as your car is driving? And it turns out the answer is no. There's actually traction maintained between the surface of the road and your tires. The tires are actually just rolling over the surface of the road. So there is static friction holding the tires in place. Okay? Static friction between the underside of your tire and the road. So the way static friction works is, of course, it's given by an inequality. It can't ever exceed mu s times n. So this means if you try to take a turn too fast, static friction won't be enough to hold your tires to the road, and then you'll start to skid. So you can only take a turn at a low enough speed before you start to skid. So let's look at an example of this. The example here says, on a dry day, the coefficient of static friction between your car's tires and the road is 0.6. So that's the static friction coefficient between, let's say, the rubber and the concrete that are in contact between the road and the tires. What you're trying to do here is drive on a curved section of road that has a radius of 50 meters. What is the minimum speed that you can drive on this curve without skidding? Okay, so the picture is right here. You're driving on a curve of some radius. Okay, the radius is shown here. At some speed, what is the maximum speed that you can take the curve? That's the idea. Okay, so let's work it out on the document cam again. And so now, what we want to do is look at this car that's driving on a flat section of road and making a turn, and consider the different forces that are acting on it. Okay? Well, one that we can immediately identify is the force of gravity or the weight. So W is a vector pointing down. The other is the normal force from the road. Now, we're assuming the road is perfectly flat, so that means the normal force should be pointing straight up. Okay? If the tire were on some kind of ramp, this wouldn't be the case, but it's on flat road, so we have W going down and N going up. Of course, that's not the end of the story. We need some kind of force, again, that's pointing in towards the center of the circle that the car is driving in. And that's going to be our static friction force. So we have our static friction force pointing in this direction. And again, that keeps the car moving in a circle. So let's indicate on this diagram what our directions are. We have Y going straight up, and then we have R going in towards the center of the circle. So that's our Y direction, and that is our radial direction. And just like before, what we're going to do is apply Newton's second law. Apply Newton's second law to both directions. So how about we start with the Y direction? The net force in the Y direction is equal to the mass of the car times the acceleration of the car in the Y direction. And if we look at the left side, we have two forces that add together. Okay, we have a normal force going straight up, so that gets a positive sign. We've got the weight going straight down, so that gets a negative sign. What does that equal? Well, it equals 0 because the car is not accelerating in the Y direction. If it were, it would be being lifted off the road or somehow crashing down into the road. But if it's just staying on the road, there's no acceleration in the Y direction. So we can set that to 0. What does this give us? N is equal to W. The normal force is equal to the weight. They balance each other out. And the weight is equal to mg. So the normal force is equal to m times g. Pretty simple. Okay, we can also do this for the radial direction. So this says the net force in the radial direction is the mass of the car times the acceleration in the radial direction. And the only force that acts in the radial direction is static friction. That's Fs. It's the only force that appears in this equation. Now on the other side we have m. And as before, since this thing is moving in a circle, the acceleration is v squared over r in the radial direction. Okay? So this is pretty similar to the previous problem. We have a static friction that needs to be maintained. We need this much static friction to keep the car moving in a circle. We need this much normal force to keep the car on the ground. And then the last piece of the puzzle is to use our static friction inequality, which says that the force of static friction is always less than or equal to mu s times n. And all we're doing here is plugging in what we derived for Fs and n into this inequality. So for Fs we have mv squared over r. That's less than or equal to mu s times n, which is equal to m times g. Okay? So we're going to take the mass and cancel it out. And then we're going to multiply through on both sides by r, which gives us v squared is less than or equal to mu s times g times r. So now notice something that's happening. Instead of getting a maximum speed like the previous problem, it looks like we're getting, let me say that again. Instead of getting a minimum speed, like in the previous problem. In this one, we're getting a maximum speed, because the speed has to be less than or equal to something, okay? So to get this maximum speed, we're basically going to take the square root of what we have on the right side, which is mu s times gr. This means this is the maximum speed that you can take this turn. Okay, this is the maximum speed you can drive on this curved section of the road without skidding, okay? Without static friction being unable to hold your tires in place. Okay, so we can calculate a number for this given everything we were told about the situation. Mu s is equal to 0.600. G is equal to 9.8 meters per second squared. And then the radius of this path happens to be 50 meters. What does that give us? A maximum speed, if you calculate this number, of 17.1 meters per second. So as long as you're staying below that speed, you're good. You're not going to skid off the road. But you don't want to exceed that speed because you will actually skid off the road if you try to take this turn. Okay, so that was that example. I want to follow this up with a question for the class. And again, the way I want you to approach this is listen to the question, read the question, then pause the video, and then see if you can work it out. Then come back to the video, and then we'll look at what the actual answer is. Okay, so the question says, it's now raining, and the coefficient of static friction between your car's tires and the road has been reduced to 0.4. So there's less of a static friction coefficient than there was before. That's what happens when the road is wet. Okay, and US just goes down when the road is wet. If you want to drive on a curved section of road with a radius of 50 meters, just like before, and you want to go 35 miles per hour, okay, that's the speed you want to take the turn. Are you going to be able to make it without skidding? That's the question. So again, pause the video, think about this, try to work it out, and then we'll come back to it. Okay, so actually, we can just use our Vmax expression from before. We know that Vmax is equal to the square root of mu s times g times r. So we can calculate this, and it's going to be something different from before, because of course, our mu s value has changed. Instead of 0.6, which is on a dry day, it's 0.4 when the road is wet. So 0.4 times 9.8 meters per second squared times 50 meters, all under the square root, gives us our Vmax. Okay? So you make that calculation, and you get 14.0 meters per second. So you have to take the turn slower now because the road is wet. And actually, let me just label this. 17.1 from before was on a dry day. Now this is on a wet day. Okay, so basically that's our Vmax, and we want to compare that to 35 miles per hour, which is how fast you're moving as you take the turn here. So what we need to do is convert the units from meters per second to miles per hour so we can make that comparison. So we have 14.0 meters on top, seconds on the bottom, and we're just going to multiply by some conversion factors to get this in miles per hour. Okay? So here we go. First one is going to be 60 seconds is equivalent to 1 minute. Cancel out seconds. 60 minutes is equivalent to 1 hour. Cancel out minutes. And then finally, our distance unit of meters, 1,609 meters, is equivalent to 1 mile. So cancel out meters. Now we're in miles per hour. So how many miles per hour is this? Turns out it's about 31.3 miles per hour. And what that means is you're not going to be able to safely take the turn going 35 miles per hour. The maximum speed you can be going is this, 31.3 miles per hour. So yeah, you are going to skid off the road if you take the turn at that speed. That's not safe. Okay, so with that said, let's go back to the lecture. And now let's talk about something called banked curves, which I'm sure all of you are familiar with because We've all been on a highway on-ramp at some point, okay? So basically, this is a banked curve right here. Instead of the road being flat, the road is now banked or inclined at an angle, okay? And there's an advantage to having a banked curve, which is you can take a turn without static friction having to hold the car in place, okay? If there's a banked curve, now there's going to be a component of your normal force from the road, which is pointing radially inwards. So let me just give you some sense of what this looks like on a force diagram, okay? This shows a car which is on a banked curve. The weight is going straight down as always, but now the normal force is not pointing straight up. It's like it's on a ramp where the normal force points perpendicular to the ramp, and it's pointing up and to the right in this picture, okay? But notice how there's a component of this normal force that's pointing this way, to the right. Well, if I'm pointing to the right, I'm just pointing towards the center of the circle that this car is moving in. Because of course, if we follow the motion of the car, it's going to come out of the page like this, and then loop back around. That's what a banked curve looks like. So there's a component of this normal force that's going in towards the center of the circle, and, well, that is what we need. We need a centripetal force to keep the car moving in a curved path, okay? So you may have seen, at some point in your life, a sign that looks like this, posted on a highway on-ramp. And this is what we call the rated speed of a banked curve. Okay, so it might say, take this ramp at 35 miles per hour or something like that. The rated speed of a banked curve that you see on a sign, it's actually the speed that you can drive on the curve without any friction necessary between the tires and the road. So you can actually take the turn with no friction at all between the tires and the road. And that's the rated speed. Okay? So let's get into the rated speed. How is this actually calculated? We're going to actually derive a formula for this. So here's what you should be thinking of in terms of a banked curve. Again, you have your car, which is on this banked curve, and the curve is banked at some angle. We'll call it theta for now, but we can plug in a specific value whenever we need to. And what we have is two directions of motion. We're going to have the y direction going straight up, and then the radial direction going straight in towards the center of the circle that the car moves in. Okay. Let's do a free body diagram of the car. Just like before, we have the weight going down, and then we have the normal force pointing perpendicular to the surface of the road. Okay? And of course, what we have are two directions of motion. The y direction is going straight up, and the radial direction is going in. Just said that. So what do we do next? We break these forces that you see on the diagram into components. Okay? There's going to be a y component, and there's going to be an r component of each one of these forces. So notice that the weight only has a y component, right? There's no part of this that points along the r direction, but the normal force has a y component and an r component. Okay, and let's label those right here. This is the y component going straight up. This is the r component going to the right. So first thing we should do is figure out those components. And the way we're going to do it is by thinking about the definition of sine and cosine, basically. Because if you look at this angle here, okay, the sine of the angle is equal to the opposite side of the triangle over the hypotenuse. Okay, and we've just constructed a right triangle where the opposite side is NR, that's right here, it's opposite my angle theta. And the hypotenuse is the long side right here, which is just the full magnitude of the normal force. So that's what we have. Opposite NR divided by hypotenuse N. Which means, when it's time to write down what NR is, it's just going to be N sine theta, the magnitude of the normal force times sine of the angle of the embankment. Now we can do the same thing with cosine, which is the adjacent side over the hypotenuse. In this case, the adjacent side to our angle is NY. And the hypotenuse, just like before, is the magnitude of the normal force. So here's what we get. We get NY divided by N for the cosine of the angle theta, which just gives us, if we multiply on both sides by N, throw it over here, N cosine theta. Okay, so the y component of the normal force is N cosine theta. That's how that vector breaks up into components. So what can we do with that? Well, as usual, we can apply Newton's second law to the vertical direction, which is the y direction. Now, if we think about the motion of this car in the y direction, that's up and down, it's not moving in that direction, right? It's just staying at a constant height. It's not going up, it's not going down. So when it comes time to write what the acceleration is, we can set that to 0. Okay, so what do we have? We have ny, which is going up, and then we have the weight, which is going down. So ny minus w is how we sum up the forces in the y direction. And then again, because we're not accelerating in that direction, we set it equal to 0 on the right-hand side. Well, before we just said that ny is equal to n cosine theta, so I'm going to plug that right in here for ny. And the weight is always equal to m times g, so I'm going to plug that in as well. And that's all equal to 0. If you take the minus mg term and add it to both sides, throw it over here, and then you divide by cosine theta, this is what you're going to get. The magnitude of the normal force is equal to mg divided by cosine theta. So what we got by looking at the forces in the y direction is a formula for the magnitude of the normal force. It's mg divided by cosine of theta. So we've got that much. So if we continue by applying Newton's second law to the radial direction, or the r direction, well, it works just like we've seen in the previous examples. There is going to be an acceleration, and it's equal to v squared divided by r. So the net force in the r direction is equal to m times acceleration in the r direction. That gives us nr, that's the only force present in this direction, equals m times v squared divided by r. Well, nr is nothing more than n times sine theta, as we worked out looking at the triangle that we get by resolving the force vector into components. So we have n times sine theta equals m v squared over r. But from before, we have an expression for the normal force, which we can plug right in there. So we're going to plug in for the normal force mg divided by cosine theta, which we found earlier. Okay, so plugging in that for the normal force, we have mg divided by cosine theta times sine theta equals m times v squared divided by r. And you should be looking at this expression and seeing a few different things we can do to make it simpler. The first is cancel out the mass. The mass drops out. So actually, our formula is not going to depend on the mass at all. The other thing we can do is realize that sine theta divided by cosine theta is the same thing as the tangent of theta. Okay? So we're going to apply the trig identity for the tangent of theta, which is equal to sine theta over cosine theta. So on the left side we have mg tangent theta equals m times v squared over r. And as I said earlier, the next thing we're going to do is cancel out the m terms, so m drops out. And then also let's take one more step and just multiply on both sides by r. So this gives us v squared is equal to g times r times tangent of theta. So we're almost there. All we need to do is take the square root on both sides to give us v is equal to the square root of g times r times tangent of theta. That gives us the rated speed of this banked curve. In other words, this is how fast you have to drive on the curve to not need any friction to hold your car in place. That's the rated speed. Okay, so with that in hand, let's do a question for the class. So let's say we have a curve with a radius of 50 meters, and it's banked at an angle of 15 degrees. If we're going to put a sign showing what the rated speed of this curve is, what should it say on the sign? Okay, in miles per hour. What should the rated speed be? Right, so let's work that out. Okay, so the formula that we just derived for the rated speed is equal to the square root of g times r times tangent of theta. That is the rated speed of the banked curve. All we're doing here is plugging in what we know, which is the square root of 9.8
meters per second squared. The radius of the turn is 50 meters. And then tangent of theta is tangent of 15 degrees, which gives us, for the rated speed, 11.46, keep 3 sig figs, meters per second. And just like before, what we're going to do is convert this to miles per hour because, of course, on a highway on-ramp, that's the typical unit you're going to see to measure speed is miles per hour. So let's go through that exact same unit conversion we did before. 60 seconds, 1 minute, cancel out seconds. 60 minutes, 1 hour, cancel out minutes. And then 1,609 meters, 1 mile, cancel out units of meters. So now we're at miles per hour. Okay. So here's what we get. We get 25.64. Technically we can keep 3 sig figs here, so we go out to the 6. And this would be in miles per hour. But the way that signs typically work on the highway is you just round to the nearest 5. So most likely what it will say on the sign is 25 mph. Okay, so that's how fast you should be driving on this particular banked curve. Okay, so that's how you do that. It turns out there's a whole lot more to say about highway curves. And just to reiterate, the formula we derived for the rated speed, it assumes that there's no friction between the car's tires and the road. Now realistically, of course, there is going to be friction, okay, that holds the car in place. So that means there's not just one speed you can take the turn in only that one speed. In reality, there's a range of speeds you can take without the car sliding up or down the embankment. Okay? So right now, we're not going to go into too much detail about this. In my notes that I'm going to post to Canvas, I'm going to show the minimum and maximum speeds here fully worked out. But for now, I just want to give you a rough conceptual picture as to what's happening. Okay, so let's take a look. Now let's say you're driving your car on a banked curve and you're going faster than the rated speed, which means, if you think about it, if there's no friction between the tires and the road, your car is going to want to drift up the embankment if you're going way too fast. Okay, it's going to drift up the embankment. So if we want to prevent it from drifting up the embankment, what we need is some kind of friction force which points down the embankment, preventing it from sliding up. Okay? So here, let's look at this free body diagram right here, which corresponds to your car going faster than the rated speed. Okay? So what do we have? We have the normal force and the weight, just like before, but now we have a static friction force pointing down the ramp or down the embankment that prevents your car from sliding up as it's going faster and faster. Okay? On the other hand, let's say you're taking the turn too slow. You're going slower than the rated speed. Well, if there's no friction, what's going to happen is your car is going to tend to drift down the embankment if you're going too slow. Okay? And in order to keep your car in place, and prevent it from slipping down the embankment, we need some kind of static friction force, which in this case goes up the embankment. Okay, so we have the normal force and the weight, just like before, but now a static friction force pointing up. Okay? So what does this tell us? Okay, it tells us you can go faster than the rated speed as long as this static friction force is holding your car in place, preventing it from sliding up the embankment. And you can also go slower than the rated speed as long as this static friction force is there, pointing up, preventing you from sliding down the embankment. Okay? So there's a range of speeds that are possible if you look at both cases. So again, in the notes that I post, you're going to see the expressions or the formulas for the maximum and the minimum speeds, but for now I'd just like to skip over that because it'll take a little bit too much time for this video. Okay? So there's a lot more to say about highway curves. And one thing we can start to think about is it actually possible for the angle of your embankment to increase and increase and increase until you're driving on a completely vertical curve? Okay, so imagine this. You drive onto an embankment like this, and as you keep driving on this curved path, the angle gets steeper and steeper and steeper, and eventually it goes to 90 degrees, which means we're in this situation shown here, where your car is actually sideways, and the road you're driving on is perfectly vertical. Is this possible? Is this possible? So actually, at this point, just pause the video, think to yourself, is this possible? Is there a way this could possibly work? And then after you think you have an answer, come back to it. And of course, the answer is yes, this is possible, as long as the forces work out in just the right way. So let's think about how the forces need to work out in this case. This is the free body diagram of a car which is driving on a completely vertical curve. Okay, so just to visualize in your head, what does the motion look like? Okay, the car is coming out like this, and the path curves around back this way. That's the vertical curve we're talking about. Okay, like this. And the y direction is straight up. The r direction is this way, which is towards the center of this curved path. And the forces that have to be acting on it in order for it to move this way are, well, we have the weight, as always, going straight down. There's going to be a normal force from the road, which points, again, perpendicular to it, so going straight this way, to the right. And then if we don't want the car to slide down the wall, we need something holding it there, which would be a static friction force. So actually, this looks really similar, if you think about it, to the problem of the amusement park ride called the Gravitron, right? This thing can move in a circle that's completely, when the road is completely vertical like this, as long as these are the forces. So it works out. Okay, so the next thing we're going to do is go to the document cam and then work out what has to hold true in order for the car to drive this way. What are the equations that go with this? Okay, so let's just get that free body diagram copied one more time. This is the car. This is the static friction force going up the wall. This is the weight going down. This is the normal force going to the right. And in terms of our axes, we have a y direction and an r direction, just like before. So what are we going to do? We're going to apply Newton's second law, F equals ma, to both directions. Net force in the y direction is equal to m times ay. Okay, so what forces act in the y direction? We have static friction going straight up, so that gets a positive sign. And we have the weight going straight down, which gets a negative sign. What does that equal? 0, because ideally there's not going to be any acceleration in the y direction. We don't want it to slide down the wall, or slide up the wall, for that matter. So static friction equals the weight, equals mg. That's what we get. Now if we apply this to the radial direction, the net force in the radial direction is m times ar. And the only force in the radial direction is the normal force. So we have n equal to m times v squared over r, because again, that's always going to be our acceleration for the radial direction. If something is moving in a circle, that's going to be the case. All right, so the last thing to do here is to remember static friction always is given by an inequality, Fs less than or equal to us times n. And let's plug everything we know into that inequality. The static friction force has to be equal to mg, less than or equal to us times m v squared over r. That's the normal force, according to what we just worked out here. So cancel out m, and then solve for v. And the way we're going to solve for v is by multiplying through on both sides by r. dividing on both sides by mu s. So we're going to get v squared is greater than or equal to g times r divided by mu s. That's what has to hold true if you're going to drive on this vertical curve. Okay? So the minimum speed you have to be going to do this, okay, because v is greater than or equal to something, there's a minimum value to make this possible. It's going to be the square root of g times r divided by mu s. So that's our minimum speed to take the turn this way. So, plugging in what we know, we have, well actually hold on, let's get back to the slide for a second because there's a problem on the slide. So again, this is our formula. You can ride the wall like this as long as you have this minimum speed of square root gr divided by mu s, just as we worked out. And then the example here is this. If the curve has a radius of 45 meters and the coefficient of static friction is equal to 0.85, what is the minimum speed to ride the wall in this way? Okay, so basically all we're going to do next is plug in these numbers and figure out what that minimum speed is. Okay, so sorry to switch back and forth so much. We have g is equal to 9.8 meters per second squared. The radius is 45 meters. And mu s is equal to, what did we say, 0.85. So that gives you 22.8 meters per second. You have to be going at least that fast. Of course, you can go faster in order for this all to work out. Okay? So 22.8 would be the answer. Again, going back to the slides here, the answer to that example question is 22.8. Okay, so let's keep it going with examples. That's pretty much all we're doing today is a bunch of examples. And the next one involves moving a ball in a horizontal circle. So let's read the question. A ball of mass m is connected to the top of a pole by a string whose length is L. The ball is set in motion so that it moves in a horizontal circle. As the ball moves, the angle that the string makes with the pole is equal to theta. So this is a problem that we're going to do purely symbolically. Okay, we're not going to plug any numbers in just quite yet. Just going to do it symbolically. And what we want to find is, given all of these numbers, the mass, the length, the angle theta, and all this, what is the speed of the ball? Can we get some kind of formula for the speed of the ball? So, before we launch into the calculation, I want to give you guys some kind of intuition as to what this looks like. So, here's a ball on a string. And what I'm going to do is swing it in a circle. And notice that the circle itself is completely horizontal. So the ball is moving in a horizontal plane like this. And so what happens, let's say, if I speed up the ball, if I speed it up a little, swing it a little faster, notice how the angle gets bigger. And then if I swing it a little slower, notice how the angle is getting smaller. So that's what we want to notice about this. Okay, the faster the ball is going, the bigger the angle, the slower the ball is going, the smaller the angle. Kind of know that intuitively, right? Okay, so with that said, let's work it out. Okay, so as usual, this is going to all start with a free body diagram of the ball that's moving in a horizontal circle. And we have to ask ourselves, what are the forces acting on this ball? Well, one of them is going to be the force of gravity, just the weight going straight down like this. But the other is going to be tension, because it's connected to a string which has some tension in it. So there's our tension force, T. W and T just like that. Now tension, we should note, always runs along the length of the string. So you can imagine the length of the string is just like this, in the same direction as the force T. And if we break these into components, because we're going to have the y direction going up, and then the radial direction going this way, because this is the center of the circle. That's the direction towards the center of the circle that the ball is moving in. We can now break the force T into components. So what do we have here? Well, the angle is theta. This is the angle that our string makes with the vertical. So that's up here actually. And then we have TR as this side, and then TY as this side. So before we do anything, let's just work out using trig how to find TR and TY. So if you remember, the sine of the angle theta is always equal to the opposite over the hypotenuse, where in this case the opposite side is TR, that's right down here. And the hypotenuse is the long side, that's just the tension, or the magnitude of the tension. So what do we get? TR is equal to the magnitude of the tension times sine of that angle. Okay, how about cosine? Well, that's always the adjacent side over the hypotenuse. The adjacent side in this case is TY, and the hypotenuse is the magnitude of the tension, just like before, which gives us TY is equal to T cosine theta. So that's just a little bit of work on the side to break the tension vector into these two components. So now that we have that, let's see what we can do next. Well, F equals ma applied to the y direction and the r direction, that's what's coming next. So you can kind of see a pattern to these problems. This says the net force in the y direction is equal to mass times ay. So what forces do we have in the y direction? Well, we have Ty going up like this, and then we have the weight going down. So those just go against each other. Ty minus W, that equals, well, 0, because there's no acceleration in the vertical direction. As the ball moves, it's not going up or down, it's just staying at a fixed height. So there's no acceleration in the y direction. So Ty is equal to T cosine theta, as we found earlier. W is equal to m times g, that's just the weight, and that's equal to 0. So what we're going to do with this is figure out what the tension in the string is using the y equation. Because of course we can rearrange this to say T cos theta equals mg, just by adding mg to both sides. And then by dividing out cosine theta, we get T is equal to mg over cosine theta. So that's how much tension there is. The next thing we need to do is apply F equals ma to the radial direction. And here's what that's going to give us. The only force in the radial direction right here is TR. Okay, so we've got TR equals m times v squared divided by r, because that's the acceleration for something moving in a circle. I've said that a number of times. Okay, so TR is t times sine theta, and that's equal to m times v squared divided by r. So there are a couple things we should do next. Now one of those things is to just plug in for tension that we found earlier, this formula, into this one. Okay, so just sub in for t. The other thing to do is think about what the radius is. Okay? Is the radius of the circle something we know if we know the length of the string? So think about this motion again. This is the length of the string right here, just however much distance there is from the point I'm holding the ball to where the ball is. That's the length of the string. But the circle it's moving in doesn't have that radius. The length of the string is not the same as the radius of the circle. Okay, so let's think about how that actually works out. This is the string, length L. Remember, the string itself makes an angle theta with respect to the vertical, like this. And then the ball moves in a circle like this. So actually, if we look at the radius of that circle, it's not the same as the length of the string. It's down here. This is the radius. This is r. And if you want to figure out what r is, well, it's going to take some trigonometry. Let's think about sine of the angle theta one more time as being the opposite side divided by the hypotenuse. In this case, the opposite side is equal to the radius of the circle. That's the side length across from the angle theta. And then the hypotenuse is the full length of the string. So actually, whenever we see radius, we should be thinking that's not the same as the length of the string, but it's the length of the string times sine of theta. Okay? So we needed to establish that. But now that we have, what we're going to do is plug in two things. Plug in this expression here that I circled for tension. Plug in this expression I circled here for the radius of the circle. So we get mg divided by cosine theta multiplied by sine theta equals m times v squared divided by r, which is L times sine theta. All right, so first thing we should think is cancel out mass, which is gone. And then let's solve for v. V squared, what we're going to do is multiply on both sides by L sine theta. So we have a g, that's already on top right there. We're going to have an L, and if we have sine theta that we multiplied to the top, and we already have a sine theta here, this can be written as sine squared theta, just two factors of that. And then, of course, we have a cosine theta on the bottom from before. And then finally, if we want to get the actual v as opposed to v squared, the speed is equal to the square root of GL sine squared theta over cosine theta. So that's the formula that we derived for the speed of this ball. So if we wanted to, we could plug some numbers in, but in this example, I just want to keep it symbolic. And that's how it works. And that's what we have on the slide there. Using Newton's second law, thinking about all the forces acting on the ball, we were able to determine the speed of it. Square root g times L times sine squared theta over cosine theta. Okay. So now I've got a follow-up question. Is it possible for the ball in the previous question, the one that's, again, moving in a horizontal circle like this, is it possible for it to move so fast that the string it's connected to becomes completely horizontal? In other words, the angle theta from before, can that actually go to 90 degrees? Is it possible in any way for this to happen? Okay. Well, first thing I can do is try to just do it. If I swing it fast enough, can I actually get the string to be completely horizontal? So the harder I try, it looks like the string moves up to a bigger angle the faster I swing it, but it doesn't look like it's ever really going completely horizontal. Okay, so maybe that's just me. Maybe I'm not strong enough to make this happen, or maybe it's actually not possible. Let's figure it out. So the way I want to figure this out is to go to our equation that we derived from before, right here, and then ask ourselves the question, what happens when we let theta go to 90 degrees? Okay, so think about that. What happens when we let theta go to 90 degrees? Well, sine of 90 degrees goes to 1, and that's just in the numerator, so that's not a problem, just having 1 up here. But the problem is with cosine theta. So cosine of 90 degrees is actually 0. So if we let this go to 90 degrees, we're going to be dividing by 0 right here, which gives us, well, an indeterminate expression, or you can also think of it as v going to infinity. Okay, so as we let the angle go to 90 degrees, the denominator is going to 0. Dividing by 0 gives you something which is going towards infinity. That's telling you the speed has to be getting infinitely big to actually make the string go at that angle. So yeah, that's not going to be possible. You can't have an infinitely fast-moving speed for the ball. Okay, so this is absolutely not possible. So the next thing we're going to do is talk about slightly different case, which is swinging a ball in a vertical circle. So before, we had the circle the ball that the ball was moving in horizontal like this. Now I want you to think we're going to swing it in a vertical circle like this. Okay, so the circle that it moves in is oriented vertically. Okay, that's what I'm talking about. So in this problem, we're going to imagine that you're holding a string whose length is 23.5 centimeters, and it's connected to a ball who has a mass of 375 grams. You're going to swing this ball so that it moves in a vertical circle at a constant speed of 2.45 meters per second. Okay? So there are two questions here. What is the tension in the string when the ball is at the bottom of the circle, so when it's down here? And then what is the tension in the string when the ball is at the top of the circle? Those are the two questions. So let's work it out. So we really want to think of this as two separate problems. Okay? One of them has to do with the ball being at the bottom of the circle. Okay? So let's kind of sketch out that circular path that the ball moves in, something like this. And then draw the ball being at the bottom of that path, the lowest point. And let's just draw the forces that act on the ball. Well, we're going to have force of gravity, or the weight. And the other thing we're going to have is tension. Now, the way tension works is it's going to be pulling on the ball along the length of the string, so it's going to be a force that looks like this. And you might be noticing that I drew the tension force larger than the weight force, and there's a reason for that. Because this thing is moving in a circle at a constant speed, we know the net force has to be in towards the center of the circle, which, let's mark it with the X. That will be the center of the circle. The net force has to be pointing in. So if we have two forces, one which is going in, which is T, the other one which is pointing out away from the center, which is W, T has to be bigger so that the overall force, when you combine the two, is going in. Okay? So what we're going to do is take Newton's second law in the R direction, as we've been doing this entire lecture, and set that equal to m times AR. It's just Newton's second law, radial direction. So now we have to be a little careful about how we do the sum of forces, because, well, we have one force, which is tension, and that should have a positive sign, because it's going inwards. Okay, let's actually label that. Going in. That's why it gets a positive sign. The weight force is going out. We consider that the negative radial direction, which is why it gets a negative sign. That's equal to m times v squared divided by r. And what we're trying to do here is figure out the tension. Okay, so I have tension minus weight, which is mg, equals m times v squared divided by r. And we're solving for the tension, so just add mg to both sides to isolate t. And we have mg plus mv squared divided by r. That's the tension if we're at the bottom of the circle. So that's the bottom of the circle. So this is something we can now directly calculate. The tension is equal to the mass, which is 375 grams, or 0.375 kilograms. That's the unit we want to be in. And actually that mass is a common factor we can just pull out. And then inside of the brackets here, we're going to have 9.8 meters per second squared. And then plus the speed, which we're told is 2.45 meters per second. We're going to square that and then divide by the radius, which is just whatever the length of the string is in this case. So that's going to be 23.5 centimeters, or 0.235 meters. So I converted everything to SI units so that the tension is going to come out in the right unit. Let's take a look at what we're getting here. If If you do this calculation, you should be getting 13.3. The units are kilograms meters per second squared, which is the same as a newton. So we can say this is 13.3 newtons. That's the tension at the bottom of the swing. So now let's take a look at the top of the circle. When the ball is at its highest point, and this will be the center of the circle right here. Up here, this will be the ball. And again, let's think about the forces that are going to be acting on the ball at this point. Well, as always, we're going to have the weight going down. But actually, we're also going to have the tension going down. Because tension always acts as a pulling force along the length of the string. So now the string is oriented this way. It's going to be pulling it down when it's up here. So the tension is going down. But what we do with this is pretty much the same as always. The net force in the radial direction is m times ar. That's Newton's second law. And when we look at the sum of the forces, we have to think, is the force going in towards the center of the circle, or is it going out away from the center of the circle? And in this case, both of the forces, T and W, are going in towards the center of the circle. So we have T, positive, again, it's going in, plus W, also going in. That's why they both get a positive sign this time, equals m times v squared divided by r. So this is actually different from what we did in the previous part, okay? Because now T plus mg is going to equal m times v squared divided by r, which means T is equal to m times v squared divided by r minus mg. Okay, so instead of adding these two things, as in the previous thing we did, we're subtracting them. So let's put in the numbers. T is equal to, the mass can be pulled out just like before, 0.375 kilograms. V squared divided by r, that's going to be 2.45 meters per second. Square that, that's V. Divide by the radius, which is again 0.235 meters. And then subtract G, which is 9.8 meters per second squared. So that's just what we derived as a formula with the numbers plugged into it. And if you make this calculation, you should be getting 5.9 newtons. Okay, so if we look at these two numbers, what's clear is the tension is lower when the ball is at the top than when it's at the bottom. Looks like we have the biggest tension when the ball is at the bottom of the swing compared to when it's at the top. So this should make intuitive sense, actually. And if you're watching this from home, just try to find something in your room that you can use that looks like this. Maybe it's a charger that you can swing around like this. Just some kind of weight or some kind of mass at the end of a string. That's what you want to do, okay? And just swing it around in a circle like this and try as best you can to keep the speed constant, okay? So don't let it speed up or slow down, just keep the speed constant. And what you're going to notice is when the ball is at the top, you feel a lot less tension in the string. It's pulling on your arm a lot less when the ball is at the top, and it's pulling on you a lot more when the ball is at the bottom. Okay, this is something you can feel directly, that the tension is biggest at the bottom and then smallest at the top. All right? So there you have it. And let's see. Okay, so I think we're going to end this lecture right here. And then in the next one, we're going to finish up chapter 5, and then maybe go through a couple example problems, but this one will just end right here. Okay?